vector spaces, right? So this is the topic that I wanted to discuss today, but unfortunately I couldn't make it to class. So we're going to look at it now here. Right, so the point here is that we are considering, we're basically looking at sets, right, where there's some notion of linear combinations of the elements in this set. That sort of makes sense. So for instance, when we were studying linear equations, it was quite natural to consider linear combinations of rows of matrices. Okay, and some of us may also have seen linear combinations of functions, right? So for example, when you're looking at differential equations and so on, it makes sense to add different differential equations and consider the combined solution and so on. And many would have also had some experience with vectors, for example, right? So in 3D Euclidean space, we have this notion of linear combinations of these vectors. That like we discussed in last class, you can add these vectors by considering an appropriate parallelogram and so on, right? So these things are there, right? And loosely speaking, linear algebra is a branch of mathematics that treats the common properties of algebraic systems, which consist of a set together with the reasonable notion of linear combination of elements in the set. Okay, so we're going to look at common properties of algebraic systems that are of this form, that they have some notion of linear combinations of elements in the set. And in this section, we define a mathematical object. So we define the mathematical object, which from experience turns out to be a very useful abstraction of this kind of an algebraic system. Okay, so we are basically going to abstract out these relevant properties into a mathematical object, and that mathematical object is what we're calling a vector space or a linear space, or also what are known as linear spaces. Right, so what we want to start with, so the definition basically requires us to define two objects. So there's the field, okay, and then there's V, which is which is a set of some objects. These objects we're going to call vectors, and the elements of the field are going to be called scalars. Alright, and we're going to specify two rules. So there's going to be a rule called vector addition, and then there's going to be a rule called scalar multiplication. Okay, so these are very similar to how we defined it for vectors as we know in physics, but we're going to capture them more abstractly. So vector addition is going to associate a pair of vectors, alpha, beta, in the vector space, and it's going to output a vector alpha plus beta in this vector space. Okay, so the sum of alpha beta is going to be, this operation is going to give you the sum of alpha and beta. And the properties that we want are the following, that addition is going to be commutative, right? So it doesn't matter whether you do alpha plus beta or beta plus alpha, the answer is the same. This addition is also going to be associative, so it doesn't matter whether you sum beta and gamma first or alpha plus beta first, the result is the same. And there's going to be a unique vector 0 in V. Yes, it has to be unique, which we're going to call the 0 vector, and it has to satisfy the property as we normally do, that alpha plus 0 is going to be alpha for all V, all alphas in V, all vectors in V. And the last property is that for each vector alpha, there is a unique vector minus alpha, such that when you add them, you get the identity or the 0 element, identity of the sum addition operation, right? So alpha plus minus alpha should give you 0. Alright, so these are the properties for the sum. Now let's look at multiplication. So for multiplication, we have the following. So this concerns a scalar C and a vector alpha, and it's going to produce C times alpha, scalar times the vector, and it must satisfy the following properties. The first is that the identity element of the scalar field times the vector should give you the vector for every vector in V. Multiplication of two scalars times alpha should be the same as the first scalar times C2 times alpha, right? So that's fine. Doesn't matter whether you compose the scalars first and then multiply with the vector, or whether you multiply the scalar with the vector first and then do the same operation again. So these two should be the same values. And finally, we have that if you add two vectors and multiply them with a scalar, then the answer should be the scalar times each vector separately and their addition. And the addition is already defined above, right? and so it distributes over it distributes over the additive property of the vector, and similarly it should distribute over the additive property of the scalar, right? So these are the two options. All right. So these are the last two properties. Okay, so this is, and it's sort of intuitive, right? These are the properties that we also see hold for the kind of vectors, vector addition intuitively that we had considered last time. All right. Right. So now note that the definition says that a vector space is a composite object consisting of a field and a set of vectors. Okay, because these are the two objects that we started with, right? So for example, there was this scalar and then there was this vector. So it's basically a composite object in that sense. And it has these two operations with those properties that we had mentioned. It is possible that the same set of vectors is a part of a number of different vector spaces, right? So vectors was the set, right? That the set V, but potentially you could have different scalars with which you could compose things. So we'll look at that in a moment. And okay, so there's a small remark about the notation. When there is no chance of confusion, we could potentially simply refer to a vector space as V. Okay, even though strictly speaking, one should say a vector space over the field F. Okay, I have to make this correction. Right? Okay. So now let's quickly look at a few examples. So there's this example of the n-tuple space Fn. So suppose F is any field, that's fine, and let V be the set of all n-tuples, x1 to xn, where xi's are scalars in F. Okay, so we're just defining a tuple of n scalars, right? And then for beta defined, for some beta some vector in F, we define addition, right? Because to define a vector space, we have to define the addition and the scalar multiplication. So the addition we define as, the addition we define as component-wise addition. So if you're adding alpha plus beta, where alpha is here and beta is here, the sum is just going to be the component-wise addition. Right? That's just the definition. And the product we define as follows, which is that if you have a scalar multiplying the vector, then this is the same as multiplying each element of each component with the same scalar. Right? And this is very similar to how we actually, how vectors behave, right, in the intuitive sense, in the geometric sense. All right, so that's one example, and one can check that it satisfies the properties that we mentioned above. All right, the next example in the textbook is the space of m cross n matrices, so which they write as f m cross n. So suppose f is any field and m and n are positive integers, then f m cross n is the set of all m cross n matrices over the field F. And the sum of two vectors a and b in f m cross n is defined by the following. So you have a plus b, the ijth component of this vector is given by the ijth component and of both a and b, and then you sum them, right? So basically everything is component wise. And similarly the multiplication of c, multiplication by c of a vector a, the ijth component of that is just c times the ijth component of the matrix, right? So this is very similar to how we defined it for the case of these fn, right? The regular vectors that geometrically that we think about. All right. So sorry, that was the second example. Now the third example looks at what? It looks at the space of functions from a set to a field. Okay, so this is sort of trying to generalize the idea that we had. So note here that in the first example we looked at basically a row vector, if you like, and then we looked at we looked at a row, right? So it was x1 to xn, and now in the second example we looked at matrices, right, with indices aij, right, as elements. And now what we're going to do is we're going to look at general functions which take you in a sense from indices to an element in the field. Okay, so for instance, let's try to define it more formally. So here f is suppose some field, right, and s is some non-empty set. Okay, so intuitively one can think of s as so intuition could be, you could think of it as indices basically. Okay, so for example, for vectors, geometric vectors slash columns, rows, S would be, like 1, 2, whatever. N, for matrices, S would be, for instance, 1, 1, 1, 2, 1, 3, and then 2, 1, 2, 2, 2, 3, and so on, right? It's just a bunch of indices. Okay, so S is just some set, right? And V is the set of all functions from the set S to the function F, right? So one can see it's very similar. And then the sum of two vectors, F and G and V, is basically defined as follows. So the sum of these two vectors, the sth component is defined to be the sum of the sth component of F and G individually, and the scalar multiplication of C with F is defined by multiplying each component by C, right? Because Fs is an element in F, so the right hand side is well defined, right? So that is sort of the idea. Okay, and right, so this I already mentioned, right, that the preceding example, so the preceding examples are special cases of example 3, right? All right. Now justification is exactly like I had mentioned, right? So this set S1 can take to be this set 1 to n, and for the second case you can take S to be the set of indices ij. Okay, so this part I think is fine because I just explained it. You can pause the video if you like for a second to quickly check that I haven't missed anything. All right, and then let's continue. So the story now is that we are going to now look at a bit more carefully how the operations in example 3 do in fact satisfy conditions 3 and 4. Right, so I sort of quickly just claimed that the prior examples satisfy the conditions. Now, since we already established that example 3 is example 3 is a generalization, right, and examples 1 and 2 are special cases, we can now look at whether example 3 actually satisfies the required conditions for being a vector space. So let's start with, I think the condition on addition is what is being tested. So we're going to check a few properties, okay? I'm not sure if it's testing all the properties. Let's just quickly see. So, right, so it's testing the properties for the vector addition, right? A, B, C. I think it's not doing the scalar multiplication part, or at least so I think. Let's find out. Okay. So, right, so one property that we want to check is Fs plus Gs is in fact the same as Gs plus Fs, right? Component-wise, we know that it's a scalar that is being multiplied, and scalars they indeed satisfy, at least for addition and also for multiplication. They're commutative, and so therefore the operation that we defined using these as the underlying operation are also going to be commutative, right? So this part is okay. The second part is saying that since addition in F is associative, well, this is also just getting induced from the fact that scalars are associative. Addition in scalars is associative, and so therefore this is going to be exactly the same function, regardless of whether you do G plus H first or F plus G first. The unique zero vector is the zero function, right? That assigns to every element of S the scalar 0, so this is fine. And inverse is exactly minus F of S, right? Because you add it and you get 0. Okay, and then the remaining properties for scalar multiplication are left as an exercise, because I should add it in the assignment somewhere. These are very straightforward things to check. All right, so let us continue then with a few more examples. The next example is the space of polynomial functions over the field F. Okay, so a polynomial function is defined as follows. So let F be any field and V be a set of all functions little f from capital F to capital F that have the following form. Okay, so it's going to take an element in the field F and it's going to produce an element in the field F again, and it has to necessarily have the following form. Okay, so it is specified as a combination of coefficients multiplied by powers of x until at most the degree well, okay, so n is the degree of the polynomial, right? So it's basically just a polynomial. And here c0 to cn are fixed scalars in f, right, which are independent of x. And this type of function is called a polynomial function. So this we know, and we know this very well, but just to be formal and clear about it. And now what we're going to do is we are going to define addition and scalar multiplication just as we did in example 3. So suppose that we want to add, so f and g, these are a poly, right? And then f plus g is going to be defined as f at x plus g at x, right? So this is basically, and then scalar multiplication is also similar. C of f of x is defined to be c times f of x, right? So it's exactly the same, nothing complicated. Oh shoot, I had it written. Okay, this was the recall. Sorry, I didn't see. Right, so it's exactly the statement. We don't need this. Okay, and then if f and g are polynomials, and the scalars c are in f, right, then it is the case that f plus g and cf are again polynomial functions, right? Because when you're adding scalars, you're not increasing the degree of the polynomial as well. So if you have a polynomial with degree n, when you add them, it's going to stay a polynomial in degree n, although this is not what it's saying. It's what we're saying is slightly stronger here. And additionally, multiplying with a scalar doesn't change the fact that it is going to be a polynomial. Right. Okay, so example 5, I have left as homework. Okay, so example 5 is saying that the field C of complex numbers may be regarded as a vector space over the field R of real numbers. Okay, so the statement is that so alpha plus I beta claim is that this alpha plus I beta can be seen as a vector space over the field R of real numbers. Okay, so I'm going to, so this is an exercise. I leave it as an exercise. The next part is the following. So more generally, let F be the field of real numbers, okay, and V be the set of n tuples alpha x1 to xn, where x1 to xn are complex numbers. Okay, the definition of addition of vectors and scalar multiplication is as an example 1, right? So which was component wise. So so I have a recall here. Oh, sorry about this. Right. So the example here is alpha plus beta is just component wise added, and the scalar multiplication is as well component wise. So it turns out in this way one obtains a vector space over the field R, which is different from both Cn and Rn. Okay. So normally, if you have elements in Cn, right, then it would just be a bunch of, so when we refer to the vector space Cn, we are thinking that the scalars are C, right? Scalars are in C, right? And when we think of Rn, the scalars are in capital R, right? But this is one of those examples where we have Cn, but the scalar is in Rn, in R. Okay, so this is why they're considering this example, and this is one of the remarks that we had made earlier, that even though the vector, right, is Cn in both cases, the vector spaces are different because the scalar being used is not identical. Okay, so that's an exercise to sort of check that it makes sense and all the properties are satisfied. All right. So and then let's continue. So we now look at some simple facts that follow almost immediately from the definition of vector spaces. So so this is I also have the definition of vector spaces. I mean, these are the non-trivial parts, right? Non-trivial as in the more involved parts. So I have them written here for our reference. So the first note is that if C is a scalar and 0 is the 0 vector, then it holds that C times 0 is 0. Okay. So if C is a scalar and 0 is the 0 vector, then C times 0 is 0. How do we see this? Because you see, it doesn't explicitly say that, right? In none of the properties have we said that the 0 vector times a scalar will give you 0. So if you can check, it's not explicitly written. All that we know about the 0 vector is that if you add another vector to it, it is going to give you the same vector. That is all we know. Well, it's how do we show this? So here's one way of doing it. So you start with C times 0. Okay, and 0 we can write as 0 plus 0, right? And this is using property 3C over here. Sorry, 3C over here, right? So C alpha plus beta is the same as C alpha plus C beta, so we can write this. And then it distributes as well, right? Wait, just give me a second, let me see. Right, so yeah, I think we did not have to use 3C yet. Yeah, okay. So I think, okay, so this first step is basically just a property of the field itself. So we don't need to use 3C. Wait, this is a property of the field, right? That the 0 equals 0 plus 0. So that's fine, we can do this. Now we can use the distributive property. So now we can use 3C, right? And 3C is going to give us the fact that we can distribute. All right, and now we have C0 plus C0, and now we can add minus C0 to both, and minus C0 we know exists because of this property 3D. Oh shoot, it was 3C, did I mess up? Okay, I meant to write 4C here, okay. Yeah, so I think the only, so this is probably fine, yeah. The only thing I wanted to mention was, yeah, this 3C part is not the correct thing to do, okay, so this is just coming from the property of the field. And then using 4C, right, which is right here, one can distribute, and then we're going to add minus C0 on both sides. This we can do using 3D, so that's the third property over here. And then this would give us C0 is 0. Okay, sorry, it's very straightforward actually. I got a little bit, I got you there through a circuitous route, but all right. Okay, and the next thing is we want to verify meaning, like, I think this I may have figured myself, so I just wanted you to check that there are no errors. The other claim is that for a scalar 0 and a vector alpha, right? So above, what did we establish? We established that for any scalar, if you multiply it with a 0 vector, you get 0, right? And now what we're going to establish is that if you're multiplying with the scalar 0 and you have any vector alpha, then 0 times alpha will give you the 0 vector again. Alright, so let's look at this. So 0 times alpha, one can write as 0 plus 0. Oh no, did I get it wrong? Oh no, it was fine. Oh man, okay, I think I just confused myself. Yeah, that's because they're using a slightly different notation. Sorry, okay, let me fix everything. I think this was correct. I had to write, so these are vectors, okay, I'm just adding the arrow for the vector so I don't get confused. Because we're using the same symbol for both the 0 of the vector and 0 of the field. Okay, so indeed we were using 3C apparently then, right? So 3C says that one can add a 0 to any vector and get the same vector. So in particular, if you add it to the 0 vector, you will get a 0 vector. So this is correct. And then we are using indeed 4C, right, over here in this step to be able to argue that you can distribute over it, and then everything else is fine. Okay, so sorry, I messed up that proof, but yeah, what is written is indeed correct. Now, similarly, one can do something similar for the scalar, right, and any vector alpha. So now, because 0 is a scalar and alpha is a vector, so I'll just put these arrows for the vector. So one can simply just add 0 plus 0, and that is fine because it's a scalar. And then one can again use 4C to distribute it, and then finally one can add minus 0 alpha, right, using 3D, exactly as we did before. And this would give us that 0 times alpha equals the 0 vector. Okay. All right. So that is the claim. Good. These are some very elementary properties, so it's fine. Okay, and then if C is a non-zero scalar and alpha is a vector such that C times alpha equals 0, then alpha has to be 0. Okay, so now it is saying that if you're multiplying a non-zero scalar with a vector and it is giving you the 0 vector, then the only way this can happen is if the vector itself was a 0 vector. Getting a bit tired. But right, the statement is that C alpha is, this is the premise, right? We're given that this is the case, and if this is the case, we're trying to say something else holds. Right, so if this is the case, then we know that if you multiply by some other scalar, say d, right, then this would be d times 0. And here, this is where we used NB1, that d times the 0 vector is still the 0 vector, and we take d to be C inverse. That's what we're doing. So that's how you get the statement. And then afterwards, C times C inverse, one can use one of the properties, right, that said that you can multiply the scalars first, and then multiply it with a vector. So this would give you 1 times alpha, and then from the property, you should get alpha, right? And so what that means is that C inverse times C times alpha is alpha, and it's also equal to the 0 vector, which means that alpha is the 0 vector, which is what was claimed in NB3. Okay, and right, so what is the conclusion of all of this discussion? Well, we are saying that C alpha is 0. If it happens that C alpha is the 0 vector, where C is a scalar and alpha is a vector, then one of these is going to happen, right, or both. So either C is the 0 scalar or alpha is the 0 vector. Okay, so those are the only two things that, so one of those two things at least has to happen. All right, and finally, if alpha is a vector in V, then multiplying alpha with -1 gives you the minus alpha vector. Minus alpha vector, remember, was defined, recall, minus alpha was defined to be the unique vector, unique vector such that minus alpha plus alpha vector is 0, right? That's how we defined it. So what we're saying is that to construct this inverse vector, it suffices to multiply with the scalar -1. And here's the proof. So you start with the 0 vector, and the 0 vector we know can be written as the scalar 0 multiplied by the vector alpha. The scalar one can write as 1 minus 1 times the vector, right? And then you can get alpha minus alpha, 1 times alpha plus minus 1 times alpha, right? This is just using the distributive property over the scalars, addition over the scalars, and then this in turn is just the vector alpha plus minus alpha, and this gives you the 0 vector. And so that in turn shows that, and because this was the unique vector, right, as was needed by the definition, therefore -1 times alpha vector should be the minus alpha vector, as we asserted. All right. Okay, and so now from the associative and commutative properties of vector addition, it follows that a sum involving a number of vectors is independent of the way in which these vectors are combined and associated. Right, so therefore basically one can unambiguously write a sum of vectors alpha 1 to alpha n, where each of alpha I belong to the vector space V. Okay, so that is the definition. Oh, sorry, that is the note. That there's no ambiguity in defining these combinations of vectors. And finally, we can talk about linear combinations of vectors. So suppose that beta is a vector in V, and we'll say that beta is a linear combination of the vectors alpha 1 to alpha n in V if there exist scalars c1 to cn in the field F, right, which is used to define the vector space, such that beta can be expressed as the following linear combination. So the coefficients are given by c's and the vectors are given by alphas, right? Or more compactly, one can write the following summation, right? Okay. And using the associative and distributive properties, one can easily write the vectors the sum of linear combinations as follows, right? So this is fine, and also scalar multiplications. So these should sort of make sense. Okay. So yeah, if you think of this as a beta A and this is beta B, then the sum is going to be given like this, right? And this is C times beta, if you like. Okay, anyway, this is nomenclature. And the remaining part, I think we already sort of covered, right? Which was the okay, so the book introduces the connection to geometry later, but in class we had already covered. We started with the geometric interpretation, right? And then we looked at in this video the connection with the abstract concrete definition of a vector space / a linear space. Okay. So yeah, I think that's about it for now, and in the next class we'll actually look at some properties and theorems of these vector spaces. Okay. All right. Thank you.